advanced material age. How materials science heralds a new class of technologies. NICOLA SPALDIN, ETH Zurich.
On the 9th of November 1989, I was an undergraduate at Cambridge and recall vividly the euphoria of my German colleagues.
Good afternoon, everybody, and thank you for being here so late in the day. I really admire your stamina. I want to start with a question. What do you associate with the term civilization? Take a few seconds maybe and tell your neighbor what comes to mind when you hear the term civilization. Does anybody feel uncivilized? I'm guessing that here in Berlin at Falling Walls, most of us are feeling pretty civilized. Some of you maybe thought of sort of the great rich history that we have here in the city, or the world-class universities, maybe. The grand literary tradition is something you might associate with civilization. Or perhaps going to the opera, somebody might be going tonight to the opera. But I would argue rather that civilization is just a measure of the state of progress in material science. And I can prove it to you. In fact, you know it already. Because from the Stone Age to the Bronze Age to the Iron Age, every major advance in human civilization was driven by a development in materials. So much so that we name our historical eras after the materials that dominated the times. Today we're living in the Silicon Age, and silicon forms the core of much of the microelectronics that enables our modern day of life. Not just our computers and our mobile phones, but communication, transportation, the list is really endless. And over the last decades, we've improved our silicon-based devices to an astonishing extent, enabling, for example, the transition from these clunky old desktop computers to sleek smartphones with tremendous capabilities, all with the same material, silicon, at the core. And we've grown used to the increase in capability and decrease in cost that's described by Moore's law. But this silicon revolution will soon be forced to come to an end as we run into fundamental physical limitations set by the size of the silicon atoms that make up the silicon material. And this means that the steady march to faster, smaller, lighter devices with more and more capability can't continue, at least not within our existing paradigm. Now, you might think that's fine. Certainly the controls on my smartphone are already smaller than I can see without my reading glasses. We heard this morning or earlier from Stefania that we maybe shouldn't be using our smartphones at all. But it actually poses a profound problem for society, because worldwide use of microelectronics is expanding so rapidly that by many projections, more than half of our energy consumption will be taken up by information technologies within a couple of decades. And this is not sustainable. If we want to maintain and expand our quality of life, then we need to take a step beyond the Silicon Age. And to take that step, we need a new material. And as a material scientist, developing that material is my job. 20 years ago, I was a young, very young, nobody laugh, postdoctoral researcher, and I was working on ferromagnetic materials. These are materials made of lined-up magnetic dipoles consisting of north and south magnetic poles. And I was working in a research group that was expert in what are called ferroelectric materials, which are materials made of lined-up electric dipoles consisting of positive and negative charges. And my plan had been to take the tools and techniques that my host group had developed for studying ferroelectric materials and to apply them to the study of ferromagnetic materials. The ferro in both of the names reflects a similarity in the underlying phenomenology between the two material classes. But what I noticed was that the kinds of materials that I was working on were very different than those of my colleagues. Ferromagnetic materials tend to be black metals like iron, whereas ferroelectric materials tend to be transparent ceramics. Barium titanate is the prototypical example. And there were no materials that fell into both classes. And this question of why are there so few magnetic ferroelectrics intrigued me to the extent, finding the answer, I'd like to say it became a passion, but it was maybe even more an obsession to me. And what I discovered was really very simple. We found that the kinds of atoms that make good ferromagnetic materials have a different chemistry than those which make good ferroelectric materials. They sit in a different place in the periodic table, and they have different arrangements of their electrons. But we were able to also show that there's no fundamental reason, no law of physics, why the two properties shouldn't be combined. And so, armed with this new knowledge that ferromagnetism and ferroelectricity in the same material was at least possible, my collaborators and I were able to develop an entirely new class of materials. We called them multi-ferroics because they have multiple ferro things in them. And we did this, basically, it was not rocket science, by taking the atoms that are good at making ferroelectricity and combining them in new materials with the atoms that are good at making ferromagnetism. We started out theoretically solving the equations of quantum mechanics to work out which atoms to include and how to arrange them. And then we simulated them on the computer to check that our proposed new materials had the properties that we wanted. And then we went to the laboratory and essentially cooked the atoms in a very sophisticated oven to make these small crystals of multiferroic materials like the one shown on the top right here. This is 0.5 centimeter. And we were able to very precisely put the atoms where we needed to have them in order to obtain the properties that we want. This is 5 nanometers, it's 0.5 angstrom, it's a power of 10 smaller than at the top, and the white dots are the individual atoms. You can see they're lined up really perfectly. So this was tremendously exciting to us. But why should you care? Why are multiferroics? Why should you be interested in multiferroics? Well, magnetic materials are complementary to silicon in many of our contemporary technologies. Where silicon is used to process the information, magnetic materials are used to store it. And they do this in opposite orientations of these magnetic dipoles I mentioned, which represent the ones and zeros of digital electronics. So north up, south down might be 1, north down, south up would be a 0. And magnetic materials are very good at this because these magnetic data bits can be very small, they're very stable, and they're easy to access. But magnetic devices come with a cost because in order to control them, we need to use magnetic fields. And to generate a magnetic field, we need a component which is large and heavy and uses a lot of energy. Maybe you once injured your knee and went to the hospital for an MRI, and you remember this enormous machine, most of its job is just generating the magnetic field to look at the inside of your knee. But now, imagine the possibility offered by a material that's both magnetic and ferroelectric. Our multiferroic materials have all of the advantages of magnetic materials, but in addition, because of their ferroelectricity, we're able to control them electrically. And compared with a magnetic field, to make an electric field, we need just a tiny component that uses a vanishingly small amount of energy. Our new multiferroics are poised to enable entirely new device architectures, new ways of designing technologies. Perhaps we're about to enter a new multiferroic age. Now, there are many factors which decide which materials are adopted in which technologies, and there are a number of competing possibilities for beyond silicon architectures. And so regardless of which material goes on to define the next stage of human civilization, I want to make the point that fundamental research in material science is important even when it doesn't lead to something that's useful technologically. This is an image of the regions of opposite electric dipole moment in one of our multi-ferroic materials from my colleague Manfred Fiebig. And the black and white regions represent opposite orientations of the electric dipole. Now, when I first saw this picture, I don't know about you, it struck me, it was kind of like when I heard my first late Beethoven string quartet. It was like, boom. Not only is it really strikingly beautiful, but it also came out of nowhere. There was nothing in my understanding of how such orientations of electric dipoles looked in a normal ferroelectric that led me to expect this behavior in a multiferroic. And uncovering and explaining the beauty of atoms and electrons in solids like this, I would say is comparable to discovering a new elementary particle at CERN, or listening to the Philharmonic play a Brahms symphony. These are all activities that as a society we find important to invest in. Now, of course, there's more to human civilization than information technologies, and there's more to material science than microelectronic devices. But materials, developments in materials, are going to be important for meeting many of the sustainable development goals that have been identified by the United Nations. Issues of the environment and climate change, for example, will only be solved with new materials that allow us to harvest clean, affordable alternative energies. Issues of food security, of water purification, need new materials for packaging, for refrigeration, for filtration. And these are difficult problems. The development of the science to solve these problems is not going to be achieved by only one tool or technique, by input from only one branch of science and engineering, but it's going to need input from many backgrounds, including the arts and humanities. It's going to need the best minds of the next generation. Teams of young people, like mine in my research team at the ETH, with diverse backgrounds, diverse trainings, who approach problems from different angles and who come with different ideas. And so, if we exclude people because they come from countries that some of our governments find distasteful, if we build walls along our borders to keep them out, if we discourage entire genders by letting them think they don't belong in the science and engineering community, if we won't work with researchers from different ethnic backgrounds than ourselves or with different nationalities, then in my research team at least, there's nobody left. Nobody left to solve the problems, to make the scientific discoveries that will make the world a better place. And that, ladies and gentlemen, is not my vision of our collective human future. But we've seen in the last days at Falling Walls that we have very good reason to be hopeful. We've heard from brilliant, creative, and diverse young people with the energy, the ideas, and the skills to solve the global problems that we face. We've seen their creativity, we've seen their energy. And so I'm going to end with a challenge to all of you young labsters and young entrepreneurs from the Falling Walls Lab and the entrepreneur activity. And this includes those of you who are watching up in the video feed. You're not let off the hook. I challenge you to build on the breakthroughs that you've shared with us and to pursue your ambitious goals with all of your energy and passion. I challenge you to not get discouraged when it gets hard or it gets boring or people tell you it won't work out. And I challenge you to break down all of the walls that stand in your way. And for meeting this challenge, I and all of us here at Falling Walls thank you, because through your commitment and your effort, you will create a better future for humankind. Thank you for listening.